One. So before starting, I've been told that I should say that if any student wants to sign for the certificate, the page should be over there. So maybe we can circulate it. Al final. Oh, at the end, sorry. If not, you leave. Okay, so it is my real pleasure to have here today with us Professor Junfa Zhu from the National Synchrotron Radiation Laboratory, which belongs to the Chinese Academy of Science. So he did his PhD in physical chemistry at the USTC, the University of Science and Technology of China, in 1999. Then he was traveling around the world as a postdoc. He was in Austria, Germany, and finally in the US, in Washington. And then he came back to the National Synchrotron Radiation Laboratory in 2006, where he joined as professor. And there he was in charge of developing new beamlines for the synchrotron, and also developing his research lines, which mainly focus on surface chemistry, surface science, and applying surface science characterization techniques, advanced surface science characterization techniques, including synchrotron radiation facilities. So he has co-authored more than 500 papers, which accumulate more than 50,000 citations, and an H index of above 110. And he's editor-in-chief of Advanced Characterization, and also editor in Surface Science Reports and Surface Science, a part of other journals in the field. So it's my pleasure to have you here today, and just looking forward for your talk. Thank you very much.
Okay, good morning, ladies and gentlemen. So it's great. It's really my great honor to be here. Thank you for Carlos' invitation and also the kind introduction. So yeah, I'm coming from the USTC, the University of Science and Technology of China. So this National Synchrotron Radiation Laboratory belongs to the USTC. So the USTC is the only university that in China has this giant scientific facility. Okay, yeah. So where is Hefei? Because I come from Hefei. So if you come from Madrid to go to Hefei, and then you can, if there's a direct flight, well, takes like 14 hours, 50 minutes. But usually you go to, from Madrid, has a direct flight to Shanghai, which is Shanghai is a little bit close to our city. So yeah, so no, sorry, this is wrong. Okay, yeah. So this is so this is our university, and this Shanghai is here. So we are close, but Beijing is here. Okay, you see, Beijing is much farther. But usually from Shanghai to Hefei is like 600 kilometers. If you take a high-speed train, it's about 2 hours. And if you take a high-speed train from Beijing to Hefei, this is 1,000 kilometers. It's like the farthest train is 3 hours and 3 hours and 30 minutes from Beijing to here. Yeah, Hefei is located in Anhui province. This is the capital city. So it's now it's the sub-central city of Chinese Yangtze River Delta urban agglomeration. This is the Chinese government defined. Okay, so this is the very important now become a national scientific research and education base. And we have this is 4 counties, 4 districts, and 9 million people here. And this is the USTC campus, one of the USTC campus. So now I'll give you some data. USTC is actually was built in 1958, and then from 1970 moved to Hefei. Now we have 6 campuses, so located in different area of Hefei city. Even we also have a campus in Shanghai and in Suzhou, and we have only 800 undergraduate students. So each year we only recruit like 2,000 undergraduate students, but we have 10,000 graduate students, and we have a lot of these partners from different countries and different a lot of this national level research institute, and you can see these are very strong actually in university, in Chinese universities. So according to this ranking, now we have number 7 in China, and also the Ledge Index, the USD is number 1. Okay, yeah. So my research group. So in my group, I do a lot of research on the device-based interfaces studies. For example, this is based on the photovoltaic or light emitting devices. We study in situ the interface between with the metal electrodes formation on top of this functional, let's say, materials like conjugated polymers and for the perovskite materials and so on. So another research project in my group is the model catalyst. So we study the oxide-supported metal nanoparticles, and then we grew the zinc oxide films on top of metal substrates, and then we put the metal nanoparticle on top of it, and then we study the interaction between metal and oxide. And we also use like CO or water, or CO2, whatever. This is kind of probing molecules to try to understand, where is the active center and the reactive mechanism. Then I have also the on-surface chemistry. So basically, we use the organic precursors to form this carbon, low-dimensional carbon materials. So this is what we'll talk about a little bit today. And then I also had, because I'm in synchrotron, in the synchrotron we have to do some instrumentation and metrology, things here. So I built up 2 beamlines in Hefei light source, 2 beamline and stations. And now in the Hefei, in the new facility, I was in charge of the 1 beamline and the stations. So this is we'll talk about later. So today my talk will basically to introduce some examples about what we did in the past to synthesize these graphene nanoribbons on surfaces, and then at the end I will briefly introduce this our synchrotron facilities. That's in the future. I hope we can build up some kind of collaboration, with the institute. Okay, yeah. So the graphene, I guess I don't have to talk about too many things. It has very unique properties. So because of this unique properties, these guys win the Nobel Prize in 2010. So I guess yeah, I don't have to speak too much about this. But if you use one graphene, you want to really use it, you have to open the band gap. There's different ways to open the band gap. First is the reduced dimension. For example, you can go to cut the graphene into the graphene nanoribbons or graphene nanosheet, or you can introduce lumpens or rings or heteroatom doping. So and then the process you can also introduce the pores inside like this and spin introduction. So I want to mention briefly about this. So you can see this graphene nanosheets. If you reduce the dimension, you can see the open the band gap. Okay. This is one example, and then you can you can also cut the graphene into the graphene nanoribbons. Here I show that the graphene nanoribbons with different edges. For example, here the armchairs zigzagged, and then Carol zigzagged, and then Janus graphene. For example, this one side is zigzag edges, the other side is different. And then here we can also synthesize like armchair Janus graphene. Okay, so this Carlos knows. Carlos, knows much well. So this is from Roman Fassel's group. They did the first graphene nanoribbons on surfaces. So this paper has been cited more than 4,000 times, more or less. And then the same group also used different precursors. You can see here from armchair edge graphene nanoribbons. Here's zigzag. So with different, if you design different precursors, you will finally get different nanoribbons with different edges. Okay, so I don't want to spend too much on this. And then my friend Jung Yu from Singapore, the recent years they fabricate this ferromagnetic graphene nanoribbons, like basically use a different precursor. You can see here, then that they can get different width of this thing. They introduce spin on the surfaces. It's called the so-called Janus graphene nanoribbons. And then you can also make these metallic graphene nanoribbons on surfaces. You see here with these precursor molecules. So this microchromy in his group, and then you can use STS to demonstrate that it is the metonic stages here. So I also briefly, and here this is also beautiful work. So they do this precursor molecules first. The warm and coupling form this nanoribbons on the surface, and then we further increase the temperature, the cyclodehydrogenation reaction happened, and then you introduce pores there. You can also you synthesize the porous graphene nanoribbons with doping like a nitrogen surfaces. You can really tune the structure, and then this lump benzene rings work. So this, for example, this is microscopy group. They use this 5-7 precursors, and then first the warm coupling that forms the ribbon, and then with further increase, and then the lateral fusion, happen, and then form this only with the nanoribbon with only non-benzene rings. And here Carlos, they did very beautiful work also here with 755 work. So this is also, you can see that I didn't show that, but the band gap is only 1.543. And here you can also introduce doping the different elements inside acceptable carbon. So you can see indeed they can tune the band gap here. So this is just the background. I want to just tell you that how we can tune the band gap of the graphene. Okay, and today I want to introduce a work. First is we use this dibromine biphenyl precursors, and then here is tetrabromine. So it's because this precursor you draw the solution like this, but these single bonds actually the molecular precursor can rotate. So at the beginning we want to see whether it's possible to form graphene nanoribbons on the surface. And in the solution-based chemistry, you can see first for the tetraphenyl, planar this and equal this, so the non-planar saddle shaped. So this is solution-based. So on the surfaces, we think whether it's possible to form this same structure, but it's planar, and then if you further heat the temperature, will form this structure. So this is the synchrotron radiation photoemission tells us that this precursor molecules, if you put on the silver 111, immediately start debrominated reactions happen. And if you further increase the temperature, you see that the intensity drops. That means that you have also a desorption of these molecules, with increased temperature. So, and what happens if you look with STM, see at the room temperature, you can see there's all the array form the dimers, and this dimers form is linked by this 4-fold carbon silver carbon bond, and these are the debrominated, the bromine atoms here. So this is the room temperature. You see already the reaction starts, and then if you further increase it to 450, now this all of the dimer, organic metallic dimer disappeared. So now you form these rhombic shaped molecules. If you zoom in, you can see now this is form this basically like a graphene nanosheet, on the surface. This is around it, this is the bromine atoms. So it looks like this. So we propose the reaction mechanism that this organic metallic, intermediate, and then first the interstitial silver goes away and then form here, and in the meantime activate this hydrogen here, and then it forms like this bond from this structure. Okay, and this is the theoretical calculations really prove that it is the case. So okay, so this is the first work, and now then we think these molecules, it didn't rotate like go to this direction, and then we put both sides bromine atoms the initial idea is want to see whether we can see the forms of the graphene nanoribbons, but it's actually different. Now, with the single radiation photoemission, you can see at low temperature, the molecules keep intact, but with you warm up to 300 Kelvin, this demineralization reaction happened. And then in the meantime, you can see in the carbon OS, now you can see this the peak. We actually can deconvolute this peak into two components when the molecule is still intact. So the ratio is like here this is the atom, this is carbon atom attached to the bromine, and this is the sp2 carbon. So we just deconvolute into two peaks. The ratio is 1 to 2, and the stoichiometric ratio is 1.212. So it's very consistent. And then if you go to 300 Kelvin, you see the new peak here, which is basically this carbon, silver carbon. Basically, it's organometallic, species. And then if we further go to 400 Kelvin, you can see still stay there 400 Kelvin. And then if you go further, and then it disappears. So this is the structure model which is based on the STM measurements. Okay. And I will show you here these low temperature when the molecule stays intact. These guys can self-summarize into all the structure, which is nothing, special. And then if you go to now go to 300 Kelvin, you see the STM in the XPS already the molecules, majority of the molecules debrominated on the surface, and then this. You see this trimers, tetramers, and also sometimes dimers on the surfaces. So this means that when this debrominated, actually with DFT calculated that the debrominated molecules first undergoes the intramolecular ionization reaction once this form these radicals, and then immediately the molecule is bent, and then to form this four membrane here, and then the rest two just stay on the surface. And then when you increase the temperature to 400 Kelvin, and then you see that still we have this carbon, which is the silver carbon peak in the XPS. That means you have the organometallic species. You can see from XTM XPS it's clearly that you have this broad protrusion which is assigned to the absorbed silver atom here. These are the mimic the DFT calculated the results, which is consistent very with what we observed. If you go to further increase of 400 Kelvin, now you form this thing here, and this STM tells that this Laplace field as in images you can see this formed 4 membrane, 6 membrane, and 8 membrane here. This is particularly interesting for the chemists, I think, in terms of how to draw the chemical structure of this. Here we actually analyze the aromaticity, and then you can see from here this is a single bond which is much longer, and then this is shorter, and then actually and then form a ring. And this is the 6th membrane is basically shows the aromaticity, and then here's the anti-aromaticity. So that you can really know that this is a single bond. It's a 4 membrane here. Okay, this is and also we further analyze the STS spectra to find out this band gap is like 2.9 eV, and actually if you do this the homonormal position, if you put this mapping, you can see the electron structure which is like this, and then the DFT calculator is consistent with our result. Okay, so this is the graphene nanosheet. The next one we want to show that we form the graphene nanoribbons with the help of atomic hydrogen. So the atomic hydrogen will really lower the temperature and also increase the selectivity. You can see, and so we put this is called this precursor, the DBTP molecules on surfaces. First, they formed the ribbon, which is PPP chain, and then if we go to further increase it to 650 Kelvin, now you can see this is the width getting get broader. So if you look carefully, you have this different width. You correspond to the different width of the graphene nanoribbons. This is 6 armchairs graphene nanoribbon, 9 armchairs graphene ribbon, 15, and as you can see, there are some are broader, some are narrower. Okay, so if we put the atomic hydrogen on surface, not only we can get rid of the bromine atoms with hydrogen, and then you can also super hydrogenate the PPP, and then with increased temperature to 590 Kelvin, now you have this only 6 armchair graphene nanoribbon have formed on the surface. So why is the case? Why is only 6 graphene nanoribbons? So we think first this super hydrogenated PPP chains, as we draw like here, and this both can form graphene nanoribbon. And also the other thing is the temperature is lower. Now only 590 Kelvin. So you can see the other graphene nanoribbon forms like 650. So this low temperature, there's no further fusion of the chains to this graphene. That's why we think it's forms relatively uniform width of graphene nanoribbons. Okay, so the next example that we want to show that we have found, we have observed, this 575 membrane graphene nanoribbons on the surfaces. So with this precursor, the first it occurs the Wurtz coupling happened, and then a second, if you heat up the sample, you follow the cyclodehydrogenation reaction. At the end, you will form this trans and cis. So this is actually you can see at the low temperature, room temperature. So the mainly forms is like the cis structure with further heat up, and cis structure can convert to the trans structure. And then if you go further heat up to 703 Kelvin, then you can form these two structures on the surface. And this is proved by synchrotron radiation photoemission spectroscopy. And then here the different color shows different the carbon and the atoms with different chemical environments. And you can see at the room temperature it already formed Wurtz coupling already happens. So and then you can see that this peak, with the green peak, which is only carbon peak. The blue one with the hydrogen, and you can see with the temperature this goes up. This is this reaction happen. Okay, and here is you see we formed this called the trans 575 GNR graphene nanoribbons with this atomic resolved this NC Q plus FM. So it can really shows that this is the trans the structure which I showed before, and with the STS measurement, they only shows that this band gap is like 2.0 eV, and this is correspond to HOMO, correspond to normal, and then if you do this state mapping, you can see that they do have this electronic state there, and then this is quite consistent with the DFT calculated results. And then if you do the cis, and then now the cis structure like this, so the FM tells it is a cis, and then now this becomes the symmetrical band gap increases like 2.5 eV, and this is the static mapping, and it's also consistent with the calculated result. And the DFT calculator for the freestanding these things indeed tell you that this band gap opens up from the trans to cis. In addition, you can see that this now forms this flat band on both sides, on homo normal. Okay, and yeah, this is the I think it's this is different from what you observe in the 755. Okay, yeah. Okay, so and also we actually analyze the aromaticity. So by measure the leaks and the HOMA, and you can see here the aromaticity mainly locates on the 6 membrane rings, the 575, they have choose the aromaticity. Okay. So the next sample I want to show, we embedded the pores into the graphene nanoribbons. So we use first in the literature you can see a lot of these examples which I don't have to show them here. So we use these precursor molecules and then we use different substrates, silver 11 and gold 111, and so the reaction scheme like this. So in the silver 111, you can see finally we form this with the graphene nanoribbons with 14 annulene pores, and this the reaction happened through this organometallic intermediate, and on the gold 111 we form this graphene two-dimensional graphene nanosheet, and then there's no organometallic intermediate which we observed. So instead they directly form this carboning on the surface. So here the STM result, you can see at the low temperatures when molecules stay intact, they self-sublime into very ordered structure through this carbon, through this the halogen bond and the hydrogen bond. So this is well known in the I think in the on-surface synthesis community. And then if you go to 410 Kelvin, now you see this forms the ribbon on the surfaces, and now you can see you have the bright protrusion which is due to the silver atom, and then this bromine atoms which is detached from the molecule. So this is the structure like this, okay? And then if you go to further 510 Kelvin, now you form this graphene nanoribbons with porous graphene nanoribbons, and you can see the bright protrusion on one side, the dark on the other side. This is due to this is nonplanar because you have this hydrogen repulsion in between, so that's make this up and this low, down. So this is actually DFT calculated results, which is consistent with what we observed. And now this the synchronous radiation photoemission can really help to understand the reaction mechanism. So when the molecules stay intact, this is bromine peak located here, and then now you have 3 carbon peaks, which can be assigned to these carbon atoms with different chemical environment here, and the ratio is quite consistent with in the stoichiometric ratio here. When you go to increase the temperature, so you form this carbon organic metallic species on the surface. You find this new peak here, and now you can see with this temperature when you form only the organometallic intermediate on the surfaces, we observe this peak, which is again quite consistent with what the stoichiometric ratio should be. And if you go to further carbon higher temperature, when you form the porous graphene nanoribbon, you only have these carbon atoms here. Okay, so this really helps to understand the STM result. And then now we characterize the electronic structure by measuring the DIDV mapping. This is in collaboration with my former student Qitang, because in my group I don't have the low temperature STM facility. So here you can see this band gap around 3.0 eV, and then if you do this DIDV mapping at this BIOS, and you can see that the two forms you see the local density of state along this ring. So this is the ring, and here now if we change to gold, and then again forms this well-ordered self-sublime structure, which is on same as on the silver 111 surface. But if you go to increase the temperature, now you can see immediately now you have this this carboning on the surfaces form this here, and this is assigned to, we have this gold atom in between here, and when you go these are the, if you go to further the high temperature, so now you can see here this two-dimensional sheet, and then you can 14 this 30 annulene pores on the surfaces, because they are very close to each other. So they shows nonplanar structure, which we observed here, you know. Okay, and this STM, this XPS, hydrogen XPS again to help to understand the reaction mechanism. So this is measured in our synchrotron radiation photoemission in the station, and this is result really consistent with what we observed. We propose the atomic structure. Okay, and now you measure the electronic structure over here. So this is now the band gap is about 2.9 something. And this is the mapping. So I want to, yeah. So, okay. So the last example I want to show here, we use this precursor molecules because why we choose this one, because this double bond, if the double bond becomes single bond, then this will be a 6 membrane here. Okay, and then you probably you form this open shell structure. So so we put on the gold surfaces. And you can see when you heat up, because this precursor molecules stay on the surface like this. So the one side tilt point down, the other side, both sides form on close to the surface. The other side tilt up. So then you form this called dissymmetric debromination reaction happens. So you first form this one, and then in between there's a gold atom. Here. So when you first increase the temperature, and then this warm uncoupling happen again, and then you form the porous graphene with very narrow gap in between, and then finally if you increase the temperature, and then you form this very big pores on surfaces. Here the molecular low temperature is self-summary in all of the structure, but if you go to 380 Kelvin, this dissymmetric, warm uncoupling happens. So dissymmetric this debromination reaction happen, and this now in between they have this gold atom here. You can see clearly, and this is also was proved by the synchrotron radiation photoemission spectroscopy, which I showed later on. Here you can see here, the 390 Kelvin molecular start, nearly half of the molecular debrominated because this symmetric debromination reaction happened, and then you form this this intact molecular. Then you form when you form this structure, you can see this peak. Now this intensity increases relatively. If you finally go to this, the intensity is really consistent with what we propose in this structure. And the DFT calculated results further proof that this is this is energetically favorable. So this is called a symmetric debromination reaction happened in the first step. Okay, now if you go to increased temperature, so you can see now we form this structure on the surface. Some are bright. The bright because of the you form this teal up and this is teal down. So like proposed like this. So because this in between is really narrow, so you can see this teal up. Actually, if you with DFT calculated the result, find out. The lowest part to the surface is 2.9 angstrom, which is even shorter than the normal graphene ribbons on the surfaces. That means this has a strong interaction between the substrate. Okay, and then with the SDS, the DITB mapping, you can see the band gap. You can measure from here like a 2.7, and then in between here we have this small peak is due to that interaction between the gold substrate with here. This is called a hybrid electron state near the Fermi edge. Okay, so this is the calculated result, which tells that we do have some kind of interaction with the gold substrate. Okay, and again, now this is the calculated result. Tells we have this hybrid the electron state on the gold 111, Okay, I need to speed up. And then we go to further increase the temperature from this structure, now you form this structure. This is a cyclodehydrogenation reaction happen in many of these molecules. Now this pushes this towards this direction and then open up. And this atomic result, STM results, tell it is the truth. And it is like this. And actually this is the Jimin Cai actually also observed a similar structure like this. Okay. And this is the whole structure measured from the DIDV mapping, DIDV spectra and mapping, and it tells you that this is valence band and this is conduction band, and they do have to choose this electronics properties on this voltage. Okay. Yeah, well, I think I already talked like 40 minutes. So this is the summarize. I don't want to show, but I want to thank these students who does this work, and also the theoretical calculations with this Professor Zhu Guo in Beijing Institute of Technology, and also Pavel did some calculation for us. Chen Chen is now doing this postdoc here in Madrid with David Esiha, and this guy is doing postdoc with Michael Gottfried, and this student is still in my group, and Tao Wang now also become professor in Shanghai Institute of Organic Chemistry, in CS. Okay, so now I spent like 5 minutes to introduce the Hefei light source. So this Hefei light source is like this. This is actually the first dedicated synchrotron in China. So this was built actually, the first one built like in 1990. This is second generation. It's and then this start from 2012. We completely reconstruct the new ring, and then so this is when I come back to from the States. We're actually doing now participating in the upgrade. So this Hefei light source like this. Now we only have a 0.8 GeV, which is a very low energy ring, and a very small synchrotron facility. You can see only like 10 beam lines on this here, and the blue ones are the bending magnet, and the red ones are undulator beam lines. So these are the basically you see these beam lines like infrared, because we are basically produce the characteristic of the UV and soft X-rays. So here you have the combustion flame, which is based on the photo-induced mass spectrometer, and as a mass spectrometer and the soft X-ray microscopy, and then there's spectral radiation standard and metrology, and atomic physics. This is also again, this is based on mass spectrometer. So I actually built up 2 beam lines here. So one is called photoemission and spectroscopy station. Another one is called catalysis and surface science. And here, so here one is binding magnet, one is undulator. Okay, and you see this undulator. So because our ring is only 800 MeV, so I have to use the IVU, so called the in vacuum undulator. So now it can bring the energy up to 600. So we do have this high resolution. You see here, you can ruthenium 001. We can find the surface component, bulk component, and this sulfide 2p. You can see the peak very well resolved. And then with this beam line, we have a relatively small beam size and also relatively high the photoflux. So the resolution is high, and so we have different chambers. So there's a lens chamber, and then except for photoemission, we have also except for this synchronous light, we also go equipped with the monochromatic X-ray source, which can do high resolution XPS, because our photon energy only go to 600 eV, and there we have also need TBD and this is typical, and then we can do also the lasers. So we can do the in the lens chamber. We have also the partial electron yield detector to do the partial electron mode lasers, and then also can do TY, the total electron yield lasers there. And then we have a preparation chamber, MV chamber, so we can do we can prepare sample by evaporated organic molecules and metals on different chambers. So we have these are the features we can do. The function can do this high resolution synchrotron radiation photoemission. Actually, we can also do SRPES, but because of the manipulator is only cooled down by the nuclear nitrogen here, low nuclear helium, so its resolution is not as good as the other spatial angle, SRPES and station. So we can do the XPS, lead, and also the Lexavs. Okay. So the other understanding is called photoemission understanding is based on the binding magnet. So there has a energy can go to 1,000 eV, and the resolution is relatively low, and the beam size is slightly larger. But we have also the different chambers. So we have the preparation chamber, analysis chamber, and also we have the high pressure cell, the infrared here. So we can do lead. We can do XPS photoemission Lexavs, and also we can do this. Can go to the reactor. So this high pressure, high temperature reactor can go from, let's say, from UHV to like 10 bar, something like that, and temperature can go to 650. So you can really do the real catalytic reactions there, and then without exposed to air, you can pump down, and then you can transfer sample to the analysis chamber to do synchrotron radiation for the emission or Lexavs measurement. Here the high pressure cell here, and also we have the infrared. So particularly for doing the UAG based surface science, because this is very good to do the real model kinds of studies. So we can really do a lot of reactions on surface on surfaces, and then characterize the surface structure, okay, before and after the reaction. So now Hefei is built up the fourth generation synchrotron. So this looks like that. So it's called the Hefei Advanced Light Facility, and this is already ready. So in China, right now we have three, and basically these dedicated synchrotron. So Hefei is like the 0.8, which is working up to now, and then Shanghai is 3.5. It's like a third generation. Beijing, they just built up, just finished the fourth generation synchrotron with 6 eV, so they can only go to hard X-rays. And the Hefei, we are right now going to the fourth generation, which is 2.2 GeV, and then it covers from UHV to the VUV and to the 10 X-rays. And okay, so this is the first phase. So now it's only 10 beam lines, and then the circumference is like 480 meters, and this is we're supposed to finish in 2028. Maybe next year we already start commissioning, and this they invest like 2.9 billion this Chinese currency RMB, and then if you divide by 8, then you can convert to euro, and yeah, so. The total capacity of this big synchrotron is like 35 beam lines. So for the first phase, phase 1, we only have 10 beam lines. So this is the outlet of the 10 beam lines. You can see basically they are soft X-ray beam lines, and we only have like 2 10 X-rays. This is my beam line. So I propose to build up this high flux 10 X-ray in situ operando X-ray spectroscopy beam line. So. Okay, so this is called BO08, and this is the basically the beam line, the energy range. You can see my beam line can cover from 700 to 10,000 eV. We can do the hard space, the hard X-ray XPS, and then this lab PS, so the pressure to especially look at the solid liquid interface, and we have also XS, XES, and stations. So and we want to do this is the method is covered from photoemission and XS, XES. So we want to really in the future to do the in situ and operando measurements. For example, if we have like photovoltaic devices, we want to to look at the buried interface with the hard X-ray XPS and so on. Okay, and also we can do the batteries researches. And this beamline we have this soft X-ray micrometer and double crystal micrometer for the 10 X-ray to hard X-rays. So yeah, this is the So this is the three extensions. This is the hard X-ray XPS, and this is the ambient pressure XPS, and this is the XSXES. And so this is the future. Okay, with this I want to just show this is my journal, the advanced characterization. So I hope anything which is related to this atomic resolved STM or TM, whatever, or in situ or random measurements, you can. It's very suitable for this journal. So right now, the first issue will be released by the end of this month. And now you can see this journal is open access for free. So it's open, it's free open access. This is SCI Light Australia, the publisher. Okay, and then next year I will have a conference in Suzhou, in China, Suzhou, which is close to Shanghai. This is called the 17th European Conference on Surface Crystallography and Dynamics, and also 15th International Conference on the Surface Structure of Surfaces. So this actually was last time was in Vienna. So now the community want to move to China to do it. I will do it on Suzhou. So Suzhou, from Shanghai to Suzhou is only half an hour by speed train, high-speed train. Suzhou is very traditional, beautiful city for the Chinese, the garden, culture. You see there is very nice, the buildings and so on. So we have USGC have a campus there. So the conference will be in this campus, and then we will live in the big lake in Suzhou area. So I hope many of you guys can go to attend this conference. Okay, with that, I would thank you very much for your listening, and I would be happy to answer any questions. Okay.
For this nice review and introduction of graphene nanoribbons. So we have time for discussion, questions.
Hi, Junfa. So thank you so much for your talk. I have one general question. Like, when you are dealing with these non-benzonated polymers, we see that the band gap is like our goal is to have a low band gap.
Yeah.
But at the end, when we experiment, the band gap is quite high. Like, how can you engineer this so that you can like tune the band gap, or like I don't know, because
you mean what do you mean
the band gap of the polymers?
The graphene nanoribbons.
Yeah.
Okay. Yeah. They quite high. You mean?
Yeah, like it was like 2.5. Like.
Yeah. This is the. Yeah. This is. I would say. You see, when you have this 575 graphene nanoribbons, it's lower down. It's like Carlos did this, and they. This is Carlos explained due to probably diapers, right? And then this porous graphene nanoribbons, if you compare with the same width of the graphene nanoribbons, it's actually lower. So yeah. So if it's same width graphene nanoribbon without porous, there will be with porous will be lower. Oh, will be sorry. Will be higher. Yeah, will be higher, right? Slightly higher.
Because I thought like if you introduce these like non-benzonerics, and I don't know, do you think that the conjugation is lost or something when you create this polymer, or like this? This graphene nanoribbons, or I don't know, because the band gap was I don't know.
I think what he's asking is if that is something I wanted to ask you. For example, the nanoporous graphene nanoribbons, do you have the band gap of the monomer only? Of the
Band gap of the monomer?
yeah, of what would be the monomer?
No, we didn't. I guess,
Because, for example, in our 755 polymers, what we have the impression is that basically as the conjugation is very low, because you have only single bonds, that you retain more or less the band gap of the monomer instead of. So you are like coupling monomers with low conjugation. I think that is your question, no?
You mean, for
No,
example,
in
like
the porous one.
huh?
In the porous one.
The porous one.
Yeah, this one. On silver.
So yeah.
So basically,
You mean
if you calculate the
this one?
yeah, if you calculate, because you don't have it, right? The band gap of the monomer probably is similar, no? Once you form the ribbon.
Which monomer is it? You mean band gap of this?
Yeah,
We don't know.
you don't have.
Yeah.
So probably it would be similar.
Probably similar. You think? Yeah.
Yeah.
Well, we didn't calculate it, and okay.
Okay, so thank you for a nice talk.
Thank you.
You show so many examples which are interesting. I noticed that in many cases the molecules are under stress. So, for instance, you find 4 carbons forming a square, which is stressful for a carbon bond, or even the 5, 7 rings, which also are under stress. So I wonder if that stress could be monitored somehow and used to tailor the properties that you are describing here. I remember that, I guess, Van 't Hoff said once that molecules under stress could do wonderful things for us, and maybe this is one of the cases. Have you ever think about that?
The answer no. You mean
the role of stress on
the role of stress? We didn't, and also as I told you, in my group I'm a chemist, so I only do the synthesis, and so we don't have a low temperature to further to do the physics studies or whatever. So I haven't looked at it yet, So
all right.
yeah, so it could be probably good to do, like Carlos has such nice machine. So, but I don't have this low temperature estimate. We don't further look the stress, whether the stress can induce some.
But you do theoretical calculations, right?
Yeah, theoretical calculations. They just calculate. They just try to. Well, we understand. For example, when we do the calculations, so they, for example, they do studying the band gap studies, and for example, in this 575, this memory is 57, the GNR. So we have this trans and cis. Why the band gap opens up in the case of the cis and so on. So this they're doing like this, but didn't. I don't think that they include some strain in the calculation. I don't know. So sorry.
Right. Thank you.
Yeah, I think it's well, what we have seen, for example, in our 755 ribbons with the octagon is that this stress is going to drive the restructuration of the ribbon, because they don't like to be with such an stress. So they try also to avoid. You also see, that you don't form this octagonal ring when you couple this DBBP. So these 2 benzene rings with the 2 bromines.
Yeah.
That you expect it to have the octagonal ring, but it doesn't want, and you form this other 6-member ring molecule, no? Because it doesn't like this stress, I would say.
Mm-hmm.
Questions? More questions? I have a question. So you have many non-planar things. Have you thought about applying nexavs to see the tilting angle?
Yes, I actually ask the students, but if you look at the result, if you have a really uniform structure on surface, like every ribbon, like when we point out the level and point down, then you can do it, of course. If it's some area, only a few of these things tuned up, then you cannot, you don't do it. But to be honest, students didn't do it, but actually I asked them. So they are a little lazy, to do. So I don't know whether they, I often ask, now actually force students, every student that you have to do leg ups before we really publish the results, and then to show how it looks, because the STM you can somehow cheat, you only show very small area that, right? But you see the photo emission, the reason why we do it always, every this observations we have to do photo emission, single high resolution photo emission to see whether the structure it is like we proposed, because otherwise it doesn't fit. So the leg ups is good, of course, in measurement. So the other thing is difficult things because this is a different. This is all carbon, right? Mm-hmm. If you do carbon leg ups, then you if it's like one molecule like tilted like this, you can see, okay, now this pi star, sigma star, they change. But if you have molecules with in the molecule, one side tilted, the other tilted down, you cannot really distinguish this pi star,
So you need to have homogeneity.
Yeah, homogeneity is a little bit difficult, Mm-hmm. So we do like actually when we do spin coated polymers actually, and then we do leg ups, you can see really the polymers can go to certain angle. That's really can tell. But this one, for example, this like this porous graphene here, if this tilt up, this side this is done, I think this is all carbon. But maybe we can do it with nitrogen, probably. If the nitrogen, embedded, doped here.
Or maybe using a vicinal surface so that they are all aligned.
Yeah.
And then you reduce the.
Yeah, but STM results already tell you clearly that this is non-planar. See, this with different. Here's brighter, here's darker.
Yeah. And just one final thing. So could you explain us a bit about the procedure to get a bin time in the synchrotron? So is you have two calls per year, or how does it work?
So in our synchrotron, we can submit the proposal at any time.
Oh, okay.
Yeah, so at any time. So we have in my case, it works like this. In my beam lines, okay. So we have some commissioning, beam time. Basically, you use for commission anesthesia beam lines, right? But sometimes you don't use that much, So and then this I can use this for the emergency beam time. For example, you have a paper, the reviewer said you should have a leg ups measurement. Then okay, it's good because you cannot wait. To apply for proposal to get the beam leg ups. Say okay, we just do it. And then it's very quick. So often the case like it happens often, And normally in our things, you submit the proposals, and I do the first screening, and I see this is a good this good proposal, and people, this PI really does a very nice job. So I expect that he will really get good results. So then of course it's easier. And if I think this is not interesting, it's impossible to get the results. Even there are a lot of proposals even don't understand UHV, for example. They put liquids and then want to do leg ups here. It's impossible. So we just say, okay, this is no. And we do have also community to decide. But basically, if I say yes, normally, because I do this first screen already, so this is interesting.
You have the fast track.
Yeah. And then, of course, then I as a friend, I always have the priority to shift, the beam time, to get it easier,
Okay.
So so in the future, if we can apply join the project between China and Spain, for example, whatever CS or 2 years, things we can we can measure this thing. Within China, all these similar facility. I have friends, you know, it's easier to get the beam time. You know.
Okay.
Okay.
Good. Any other question? No? If not, we thank Junfa again.
Thank you very much. Okay.